welcome back all the participants for the third session of the day. Uh, I will like to take this opportunity to introduce our expert speaker for this session. Uh, Dr. Raju Sharma is currently pursuing his postdoctorate from the Department of Urban Construction Engineering at the Incheon National University in South Korea. Before pursuing his postdoctorate, he was working as assistant professor at Thapar Institute of Engineering and Technology, where he completed his doctorate in the area of rehabilitation and retrofitting of structures using advanced concrete. He has also worked in the industry as a structural engineer. Dr. Raju has keen interest in the area of repair, retrofitting, and strengthening of structure, high performance materials, microstructure characterization, advanced strengthening measures. He is currently researching on the area of efficient and economic material for structure retrofitting, repair, and rehabilitation. With this brief introduction, I would like to invite Dr. Raju to initiate this session.
Yeah, thank you, Sanchit, and thank you to Professor Dr. Sandeep Chaudhary to give me this opportunity to share some of the views regarding the sustainability, regarding the economic, aspect of, materials and infrastructures. As I say, it's better to say infrastructure, economic infrastructure with sustainability and the focus was on durability of the concrete. So as I am going to give this particular this presentation on agricultural waste utilization for sustainable construction, means sooner or later it will be connect with the structural performance and durability and all the basic concepts always be same. You want the this performance of the concrete in terms of mechanical properties, in terms of ease in work, you can say workability, and then durability is very important aspect. Everything is going to be connect with that particular aspects. Those are the basics, but the way you are engineering your concrete mix, that is basically the the modified or the challenging issues nowadays, because now the concrete and infrastructure development is mostly connected with the sustainable growth of the infrastructure rather than making a skyscraper and strong infrastructure. So let's start with this particular presentation on which I will focus on the agricultural type of waste, and I will try to connect, I will try to give you a holistic approach of this waste with the other waste, and then we will connect it with the performance criteria of the concrete. So in this particular presentation, we will see that the agro waste or agricultural waste types. Then we will see the what are the important parameter consideration while selecting agro waste, and then use of agro waste in eco building materials, and then finally I will give you the glimpse of the UN sustainable development goals, because of though these goals only this sustainability came into existence in the last 1 or 2 decades in the field of civil engineering. So we now it is the right time to get aware ourselves with this particular SDGs, basically related to those, basically with those which are related with the infrastructures. So and then we will conclude with the summary. So if you go with the agro waste or agricultural waste, we have various types of waste. We have rice husk, as in world, India and China, producing the most of the quantity of rice, and that will be export to all over the world. And with that, we have the consequences of producing those as in terms of waste, and that waste is in we got it in the terms of various varieties, and we have to handle those varieties of waste associated with rice husk. Next is sugarcane bagasse ash. This sugarcane is also produced in very high quantity in India. So the waste associated with that is also, a challenging issue to handle, right? And then is oil palm shell. It is not something which is uh, more produced in India. It is basically in Malaysia and in that kind of regions, nearby regions, that those countries are very much, interested in utilizing this particular waste, and they have successful of using this particular waste. Then we have groundnut shell, then we have tobacco waste, we have coconut shell, we have wild giant reeds, we have sawdust, we have corn cobs, we have cork. So we have the various varieties of agro waste, and it is not like that all the waste have the equal proportions of uh, importance or weightage to use in a concrete. It is just that various researchers try to utilize those waste based on their own local problems, because some of the countries have major problem with the rice husk ash, some of the countries will have oil palm shell. So basically based on that, it is a global approach, it's a global view which I am giving to you, that different type of waste is there. So if you see this sugarcane bagaceas, we never thought about that this kind of heap, industries are facing with this kind of waste produced from the, sugarcane bagaceas. And as a, as we talk about with the organic, kind of state, you know that will not lead to any success if you use that particular product in a concrete or in a cementitious material, because that organic material with the period of time degraded, with the environmental factors, and then left with the voids inside of the concrete. So there is no use of using a direct in a state of organic state of this particular material in the concrete. So various challenges was associated with that. Then people, in the lower side image with the red, this arrow shows you the transformation of this product into the concrete by making an ash, right? So when we produced this particular waste by ash, by burning it, right, you get a kind of material which are very much likely to be working as an cementitious material, right? So that particular product we are looking for using in the concrete. So this is one of that particular thing. And the next is, I'm just showing you the images that so that you will be more familiar with that. It is groundnut shell. Some of the countries are facing this kind of things because they're producing more this groundnut shell. Somewhere sawdust is there, right? So this is again people use that thing in a concrete. And then wild giant reeds, this is also used as a ash in the concrete. Tobacco waste is also used. And then rice as ash, you can see the transformation, the stages associated with the different type of waste. As I told you, the first waste we produced, that is the rice husk only. That husk is, no no advantage in using, no advantage of utilizing in a concrete as a sharing materials. So there is no use of using that rice husk, right? As I told you, the factor, it will degrade over a period of time with the in the presence of aqueous solution of concrete. So you have to convert it into the ash, and then you have to use that particular product in a concrete. Then next to the cork, some of the countries have used lots of this particular product, so they're trying to utilize that in the concrete. Right now, next is, we will just give in a brief that sugarcane bagaceous about that. The fibrous residue, the residue which you saw in previous images of sugarcane, that is about 40 to 45% after utilizing that, taking the juice from there, and then we known as that bagasse. And the bagasse are refused as reused as fuel for heat generation. That particular bagasse is used for the fuel generation in various kind of means heat generation in various kind of industry. And once it consumed, then it gave you ashes, which is approximate having a volume of 8 to 10%, right? So that we say it's a sugarcane bagasse ash, right? So the production of sugarcane is more than 1,500 million tons in the world, and is in India about 10 million tons of sugarcane bagaceas are treated as a waste material. So as I told you, the amount of waste, if increased, then it become a problem for any country. If that amount is very less for different countries, then they will not concentrate of using that particular product in waste until unless that gives you a very high or very good results or benefits. So the point is, it can be used as a fine aggregate replacement, means it act as a filler. It may act as a filler. So in concrete, to mitigate the disposal problem as well as to minimize the use of natural aggregates. So here the point is that you can replace with the fine aggregate, you can replace with the cement as well, because if we replace with the fine aggregate, then it means that we are thinking like it is act as a filler material, or somehow if the particle size distribution is different than the sand, then it may gives you the particle packing in the concrete. But if you are thinking it is a reactive kind of material, then it will react with the hydration product, and it may help to increase the strength of the material. So it depends on that how you are treating this particular waste in your research. Or if you are replacing this particular material with the cement, you might not achieve a higher percentage replacement. You have to sacrifice with the performance. If you replace with the fine aggregate, you can lead to some higher extent of replacement, and you still get good results in that. So that can be a one point here. If you say about the groundnut shell can be found in large quantities as agriculture from waste in Nigeria, producing up to 2.67 means 2.7 million metric tons per year. And groundnut shell is already used for developing roof sheet materials, sandcrete blocks as cement replacement and as a fine aggregate replacement in concrete. Now, next is sawdust. We saw that as a waste sawdust. So sawdust is the main component of particle board. It has a variety of other particles uses, including serving as mulch, an alternative to clay cat litter or as a fuel. The use of sawdust for making lightweight concrete has received some attention over the past years. And then Mageshwari reported and Vidivili reported that as a substitution material for natural sand, sawdust as might be the right choice as fine aggregate in concrete. And then wild giant weeds is also as an aggressive wild agricultural species which can be found all over the world. It has a hollow, rigid, woody stalks which are nearly 1 inch in diameter and can grow over 13 feet in height. So some of the people are using that particular waste also in a concrete. Then rice husk is one of the fundamental agrarian waste, obtained from the external covering of rice. You know that when you uncover, and the remove the cover from the rice grain, and then you got this particular rice husk, and not exactly rice husk can be replaced in the concrete, but you can use rice husk ash with the concrete up to 10% replacement. But the point is here the physical and chemical properties of rice husk matters a lot. So what in my presentation I will show you, I will emphasize on the how the physical and chemical properties affects the properties of the final product, and how what are the parameters, what different parameters you have to look into while using or considering these type of waste to producing concrete. Next is a cork. Cork is a renewable resource. It is natural lightweight cellular material separated from the bark of cork oak trees. Variety of analyzed utilizing cork as a part of construction industry, mainly in cement mortar, because of its unique composition and cell structure, which gives low density, low thermal conductivity, good sound absorption, and water resistance. Right. Now, next is the tobacco waste. So, tobacco maybe is not, much concentration for some of the countries, but some countries where it is highly concept means used, there they are looking for the solution of that. So when you go for tobacco waste, that can be used for the lightweight concrete rather than the normal concrete. So to produce the lightweight concrete, tobacco waste can be considered as a good ingredient. But if you go for the normal weight concrete, if you want to produce a normal weight concrete with that, you cannot produce that because the specific gravity is low and you cannot, produce that same amount of weight by using that particular tobacco waste. So low density and low compressive strength you can get from the tobacco waste, and now which is used in isolation. Middle density and middle compressive strength concrete used for briquette producing, and the carrier lightweight concrete are used in construction foundation and supporting part, right? Then next is the corn cob. The corn cob has silica oxide of more than 65% and a combination of alumina and silica of more than 70%. This means that corn cob ash can be used as a cementitious material in blended cement concrete. Although the use of the ash of this waste in concrete technology started more than a decade ago, the use of corn cob grains as aggregate is only recently developing. So here some of the I will brief this particular discussion here, which is important here to conclude this particular 5 6 slides. You have seen that various types of waste are available with us, you know, and we have different form of waste also with us. It may be a kind of direct waste after using the product, and then we use that particular waste product again for fuel, for getting the fuel, as a fuel, and then again the waste produced from there and amount is decreased, and then we use that waste. So you can see that it is looking the problem into the different ways. Means it is a kind of engineered problem where you are going to get the material and you are making that material suitable for the different applications. If you want to produce a lightweight concrete, it's okay to be used as a tobacco waste. If you want to get a high strength concrete, then with tobacco waste you cannot produce that particular concrete. So what is the best solution to get the high strength concrete? You have to go with the rice husk ash. Means people are using that particular waste in a ultra high performance concrete development, so you can produce with that. So it's a kind of, nothing is you can say not usable as an ingredient in concrete. Everything can be used, but you have to look the application of that particular product, what you want from that particular thing. If you want lightweight, you have to use that particular kind of waste material. If you want to use ultra high strength concrete, means if you want to get ultra high strength, then you have to see the waste in the different way, from the some in-depth, you know technical parameters. So what are those parameters? I just make this presentation as in different segments to connect with the previous general discussion to the technical aspects of this particular waste. So we will move towards the important parameter associated with the use of agricultural waste or agro waste in concrete. Okay. Now, if you see here, there is a comparison is about the sand, crushed granite, right? Sugarcane bagasse ash, groundnut shell, oyster shell (OS), and then sawdust. We have rice husk ash, right? We have wild giant reeds, right? We have cork also. So if you see the mechanical, means physical properties of these particular materials, you can see that the specific gravity is 2.38 to 2.64, and crushed granite is also having the same, but bit higher than that because it has a dense microstructure. This granite having a dense microstructure than the sand. And then you have a SCBA, right? You have a sugarcane bagasse. As you can see that variety of the this specific gravity, range of this specific gravity. That is the point where the researchers feel difficulty, you know, to standardize their results, because some of the part of the world they have lower specific gravity, right? And some of the part of the world having a bit middle range of specific gravity, and some of them have high specific gravity. So every part of the research gives the some kind of distinct results. So you cannot conclude, the results of all as a one statement. So there is a wide range of the results. You can conclude those particular, this you can say the results in some range, you can bound those result in upper limitation and as a lower limitation. Means if you say, if you see the results of this waste, you can see that always there is a, you know, statement that you can replace this particular waste in the range of this to this, right? They have the range. They never say it is fixed 10%. They never say it's fixed 15%, because they know that in every part of the world they have different kind of waste, they have different kind of mechanical properties, they have different kind of physical properties, so the results may differ. They cannot get at one particular percentage, so they always give you a range of replacement, right? So this is one of the point here, what which is very important. You can see the oyster cell is also having 2.1 to 2.48, so it is a good kind of replacement as a filler with the sand. You can see the specific gravity right here, so it can be replaced, it can be used, it cannot be used solely for producing the lightweight aggregate until you are choosing the lightweight coarse aggregates, right? By only replacing the sand with the OS, you cannot produce lightweight concrete. But maybe only by replacing the sand with the SCBA, right, you can produce the lightweight and concrete, right? RHA is having 2.03, right? Cork is, then you can say fineness modulus. So another physical property which is the most important in changing the microstructure of concrete is the fineness modulus. It can change the packing behavior. It can alter the need of binder in a particular volume. So this is something very important, because this fineness is very much related with the surface area of the product, right? And the surface area, you know that the nucleation always start from the surface when it comes in contact with the aqueous solution, and that particular surface create the hydration product on the surface. And as much as you know that you have a higher surface fineness, you can create a high strength, but it is not the straight line. it it is related with the amount of binder as well, right? So you have to change the binder as well up to certain percentage. After the certain percentage, at a fixed percentage of binder, your results may decrease, right? So this is not a straight statement. So you can see that fineness modulus of crust granite is, it act as like a coarse aggregate right here. So you can identify from here. And but SCBA is a kind of sand, 1.42 to 2.12. Then OS is 2 to 2.8, and SDA is 1.7. So you can see here the oyster shell is having a very much similar property with the sand. So if you replace that particular product as a filler with the sand, it, in the terms of physical results, it will give you the kind of similar picture, right? I'm not talking about the reaction. I'm talking about the only a physical changes occurs because of these physical properties of material in a concrete. Okay. Now, if you go with the fineness, as I told you, so this fineness also affects the property of concrete, where you can see that if you see the sand, it is lying in the range of, this upper limit of ASTM C33 and lower limit of ASTM C33. And you can compare with this range with our particular aggregate, this particular code also with the fineness code in India, and you can make this kind of boundaries with your particular sand or any fine aggregate which you are using with as a replacement with the sand. And actually it gives the good presentation in your paper when you are submitting to the journal. Okay, and if you see that the upper limit as per the British standard is very, high, very very high, means on the lower side the percentage fineness is very high they are demanding actually. So you can see that here the 100% particles are lying about 0.6 mm. But if you see at this range, right, at this range you can see that only 60% of the upper limit of ASTM C33 is here, and here you can see that 100% are passed over there. So this is the different technical aspects of different countries code, right? So they used accordingly. If you I just show you that particular fineness of the different agro waste. Here I am showing the sugarcane bagasse ash, which is calcined at 500, 600, and 700 degrees Celsius. So then they prepared this particular uh, fineness modulus of that cumulative percentage fineness, and then they got that particular. They saw that yes, the product is basically very fine as compared to the cement, right? As compared to cement, it is very fine. So one thing is very clear by looking that, yes, it will give you the packing, it will improve the packing behavior of the concrete. It is very much clear from here. The packing behavior of the concrete definitely changed when you use as a percentage replacement in concrete. But I'm not talking about how chemically but this product behave, because I do not know the chemical composition of this particular sugarcane bagaceous. So I cannot comment at this slide how chemically it will affect. But how physically it will affect, you can see from here. If you replace with the cement, more finer particles you are putting into the system, and you know you will get a more denser structure. Okay. Now, I'm just connecting those things with the some of the already established statement of supplementary cementitious material so that you can use these kind of logical reasoning in your research as well. If you see in terms of silica fume is extremely fine particle. It is spherical, it is glassy, and with an average diameter of zero point 0.1 to zero point 0.2 micrometer, right? And the specific surface area is in the range of 15,000 to 25,000 meters square per kg, compared with the value of 300 to 600 meters square per kg for other cementing materials. So these are the physical property of silica fume. Now, how you can cater this, collect this information to make the reasoning of your research. If you got some results, if you have some results, how you can say these particular reasons are: the presence of silica fume in fresh concrete generally result in reduced bleeding and greater cohesiveness, right? Reduced bleeding and gives the greater cohesiveness. This higher fineness of the silica fume that led to the higher surface area resulted in higher reactivity. Consequently, superior strength and durability is obtained, right? This higher reactivity still, being a researcher, you cannot conclude without looking into the chemical composition of this particular product. So if you say the higher surface area increase the strength, yes, this can be a good image after looking the fineness, this cumulative distribution fineness of the product, and you can say that. But without chemical composition, you cannot say it's high reactivity, although it's already fixed, already firm statement in the research. So therefore I'm using that word here without showing you the chemical composition, but I'm just saying how you can use this particular thing, right? Now we are moving towards the chemical properties of this type of waste, how we can use these chemical properties of the waste to to support our results in a research. So if you see the sugarcane bagaceous, it has the 762.43 to 90% of silica, and having an alumina of 2 to 4%, and Fe2O4 to 6.9 in 7% is there. And then calcium also 1 to 11%. So this range is very high. This calcium is very high because if the calcium is 1%, the results will be different than the calcium which is having 10 or 11% there, right? So therefore, some of the people are getting different results than the other researchers because of this kind of, difference in the chemical composition. Now, if you're looking into the oyster shell, you can look into that. You can see there is a higher amount of calcium, right? There is a higher amount of calcium. So if there is a higher amount of calcium, that can be a representative of the reactive kind of filler or reactive kind of supplementary cementitious material, right? So the behavior of this particular product is more dominant towards the hydration product formed by the calcium rather than the silica. So it is more dominant towards the calcium. It increases the calcium content of the paste And when you do the analysis, you can do the analysis of you can look the elements or distribution through the mapping of the microstructure, and by there you can do the chemical you can find the chemical ratio as well by doing the ADS on of the different of the paste at different location. And by doing so, you can qualitatively conclude that okay, this kind of you can say a phase occurs where CA by SI ratio is something different, means somewhere it is 1, somewhere it is 1.5 or something like that. You can conclude. In many research paper, you can see this statement which we are discussing here. So if you see the sawdust, it is more dominant towards the silica oxide. If you see the rice husk, yes, it is SiO2. More than 90% always the SiO2. It is only near to the 90%. Mostly people are reporting the rices as more than 90% of SiO2, and then rest of the 10% is divided into the different chemical composition. Then we have an tobacco waste. You can see here this tobacco waste is do not have this kind of the elements which we want for producing the good quality of concrete. So by this particular statement, you can see that you can say that here is a calcium is more, so it may be react with that a little bit but not more. It will act as a filler kind of product over there. Okay, now if you're looking into the palm oil, oil palm shell waste and coconut shell, and they compare, and you compare if these properties among them, you will find that the specific gravity of the oil palm shell and coconut shell is lower than the crushed granite. Yes, so it means that there is no use of replacing the oil palm shell and coconut shell with the crushed granite. If you replace that, automatically you are taking the higher material out from the system and putting the lightweight material into the system. So by seeing just, you can say the final product will be the lightweight material or light density, having a light density than the normal concrete, right? So then these kind of things you can see other combinations are there as well. So next is just an example of the small footbridge or low cost house with a floor area of about 60 meter cube, around 59 meter cube, and that is produced in the University Malaysia Sabah. To this will be the final product of the cumulative research of the different country. We can say that. Okay. Now, in more deep, if you go in the chemical properties of the agro waste. So here an example of Bagaceous, where you can see that it is an XRD and XRD of the same product, but you can see the temperature is different. Means the calcination of this particular product has been done at different temperature to look the to find out the effect of this calcination on the final product, right? So if you see here, it around this uh, 27 to theta degree, you can see a peak over there, right? Having a plus sign which shows the SiO2, right? Having an SiO2. Okay, so here you can see the SiO2 is amorphous SiO2 is increased as this temperature is increased. And then you can also see in 500 degrees Celsius, there is a almost no amount of CaSiO3, but you increase the temperature, you are getting the peaks of CaSiO3, right? So by this way, you can analyze that how the calcination, how your treatment with the waste, you know, improve the final property of the concrete. If you use 500, it may react as a filler, may act as a filler, but if you use the 700, it may react and give the kind of reactivity with the other product and increase the performance of the concrete on a macro level and on microstructure level. Now, if you go with the morphological, analysis, you can see that here they found this kind of crystal, right? And then they did some EDS on that, on these crystals, and these crystals are basically having a different temperature, right? So an extremely, extreme left side of your image is showing that this particular bagaceous is at a temperature of we can see the temperature 500 degrees Celsius, the extreme left image. And the important thing is here you can see on the table which is embedded in the lower EDS graph. Here the element is the fourth element, which is a silica, right? SiK is having a quantity weight percent of 36, atomic weight percent is 24, right? So when you move from 500 to next temperature, right? The next temperature was 600, right? So next temperature was 600. When you move towards 600, you can see the silica content in the embedded image, which is the central image, central bottom image of EDS, where embedded table shows that SiK is the weight percentage 39 and atomic weight percentage is 27. If you compare with the previous one, you are seeing that here the silica is, getting more higher. If you go with the more temperature, you can see that silica is 42% and atomic weight is 30%. So it increasing the amount of silica in the paste. It is not, I'm saying it's an individual material, right? So it increases the chemical composition of that, which may give you the advantage while using into the concrete. And yes, it is advantages here when they replace this kind of different this sugarcane bagaceous with the 10% weight percent fixed, right? 10 weight percent fixed replacement done with the cement. So SCBA is replaced with cement at 10%. The variable is the different temperature, final product of the different temperature. So at 3 days, you can see here on the left image, you can see the black one showing the reference, and then you replaced 10% with the 500 degree calcined SCBA, and then 600 calcined SCBA, and then 700 calcined SCBA. Where you can see that the 600 gives the good results as compared to the others, right? At 10% replacement with the cement, right? We are replacing with the cement. And then if you go for the 7 days, your cement is reacting, and then this uh, 600 is getting a bit down, and the 500 is getting some up, and then 700 degrees Celsius getting some down. And then if you go for the 28, you can see that this 600 degrees Celsius CVA is quite higher, little moderately higher, not significantly. It is higher than the others, right? So you can see the kind of things here, that if you treat your material with the different processes, right, under your observation, you can improve the performance of your final product. Okay. And if you see the flexural resistance in a similar way as like in the left image, on the right side, the flexural resistance of the product is increased with the 28 days curing at 10% of SCBA replacement with cement. Of course, at 600 degrees Celsius, it gives the good result. So in optimum way, because you also in your results, in your research, cannot say directly that when you have a lots of variable, when you have a different variable, one variable, you can make a firm statement, but when you have a lots of variable over there, so you have to find an optimum statement to justify your results, right? So here we can say that a 600 degrees Celsius is good at 28 days with the replacement of cement, right, at 10%. Now, if we justify the chemical composition contribution in a concrete of different material, then if I take the example of class F fly ash, especially low calcium fly ash with high carbon content or alloy, increase the setting time, right? Because the unburned carbon is considered as a LOI, and they are not as at all reactive. They are carbon content, they are not reactive, they are just act as a filler. So it's like you are making a box with the denser and denser, but those particles are not able to create an attachment, chemically attachment with each other, right? So this is the kind of scenario happens when you used high content of LOI in any waste product. If your LOI is high, that can give you a filler effect, but that cannot give you a higher means a good retention. It means like it suddenly break, right? Your composite suddenly break, right? So high calcium fly ash generally low in carbon and high in reactive and then cementitious components sometimes exhibit opposite behavior of reduced setting time. Okay, so this is the difference. Then fly ash particle consist of clear glassy sphere and spongy aggregates. Though the particle shape and surface characteristics of various types of waste material and bioproduct can be found out by using morphological tests, which are scanning electron microscopy. So by doing so, you can find out the morphological characteristics. What morphological characteristics help you? Like if you know that is the glassy sphere, it is a glassy surface, right? So the glassy surface, is help to accelerate the slippage, right? Accelerate in the slippage when it is wet. So when the material having an fly ash and it is going to flow under gravity, it is wet, having a fly ash and flowing under gravity, it flow more than the concrete which is not having a fly ash because the surface is glassy. It has a more slippage behavior, so it give you a good, this particular higher workability kind of things, I can say. A more filling effect it can give you. Okay. Now, depend upon calcium content, particle size distribution, loss of ignition, and specific surface area, right? If you say the rice husk ash contain high amount of SiO2. So well burnt and well ground rice husk ash is a very active and considerably improve the strength and durability of cement and concrete. Here the point is well burnt and well ground rice husk ash. This is the game where the product change its behavior globally, right? So well burnt and well ground rice husk ash. We will see in the next slides how this particular product means two factor affect the performance of final product. So it is very active and improve the strength significantly. Therefore, this improvement in well burnt and well ground rice husk can give you the product like ultra high performance concrete also. So many publications in the field of ultra high performance is developed with the rice husk ash. So inclusion of RHA in concrete reduced porosity and increase the amount of calcium hydroxide and amount in the interfacial zone, width of the interfacial zone between aggregate and cement base. So ITZ is very important part because it's weak. And if some of you may working in a field of ultra high performance concrete or high performance concrete, then you have seen that the statement that you have to replace means not replace, you have to avoid the use of coarse aggregate to produce the ultra high performance concrete. It is a kind of mortar, but it is uh, to avoid means when you avoid the use of coarse aggregate, it means that you are avoiding the existence of ITZ, right? When your ITZ is not there, means weak phase is not there. When weak phase is not there, the early crack formation under loading will not occur. And if it will not occur, the composite can retain higher strength, can retain higher load, right? And produce more, hydration product, right? So this is all the philosophy difference between the ultra high strength and the normal strength concrete. Now, if you go with the replacement proportions, many people did. They have done with the different codes. You have Indian Standard 10262. Now the new code is also arrived in this design mix, and there is an American code also. There is a Korean code also. There is a Canadian code also, right? So people develop those particular thing with the different design strength M20 with the 51.6 MPa and different strength you can achieved through this particular replacement level and type of cement used. There is different type of cements people used and different type of agro waste they have used. with the different replacement level. So you can see that some of the replacement goes up to 75 as well with the groundnut shell. But I haven't the result of that in terms of performance, so we cannot comment. But yes, people tried to replace the waste with the agro waste with the cement as much as they can, right? But the feasibility is also one of the point here, which gives you the limitation. Now, one of the coconut shell lightweight concrete composition is given below in the screen, where cement is 510, water to cement ratio is 0.42, coconut shell is 330, fine aggregate 750, slump is 5, and 28 days cube strength is 27, which is good strength, and density is the criteria to get the lightweight, so it is 1970, right? So but this by this way people are producing the different kind of concrete, because now we called it not a controlled concrete, we can say it's a tailored concrete, we can say it's an engineered concrete rather than saying a simple concrete, right? Now, based on this discussion, what we can conclude that yes, the waste can improve the performance of concrete, but the extent, the magnitude may differ, that how you treated your waste, right, with the different you can say processes, right? So these four things affects this performance, like chemical composition, particle morphology, pozzolanic reactivity, and fineness. So these are the four aspects where you have to learn the fundamentals of the waste to give the reasoning of your research for publishing, right? So I will just take a lead of in the RHA, because it is most popular material agro waste which are using nowadays, and they have used in the new type of concrete also, that is self compacted concrete, that is high performance concrete, that is ultra high performance concrete, that is ultra high performance fiber reinforced concrete, that is geopolymer concrete as well. So different type of concrete, and all are new, and where the Arisa's cache is successfully used. So we have seen that chemical composition of RHA varies depending on the combustion condition. We haven't seen this particular thing. We will see in the coming slides. I will discuss this thing. So I'm focusing on how combustion affects. We saw that just in the form of, I think, in XRD, the phases we have seen. So when it is burned at high temperature above 700 degrees Celsius, only crystalline silica remains. Okay. So therefore, you have seen the peaks in the 700 degree at an XRD of the bagaceous also. You have seen the more crystalline phases are there. Just a supporting a line. Only crystalline silica remains, which can be used in the ceramic and steel industry. However, when crystalline silica is exposed to air, it can be hazardous to human health by causing the disease siliceous. Hence, it has been proposed that RHS should be burned at low temperature, right? So this is the philosophy of using this RHA. RHA produced by controlled combustion is a porous material containing a high concentration, more than 90%, I say, this content silica. The optimal combustion temperature for obtaining the highest content amount of silica is range of 500 to 700. I told you this is the range. You cannot get a good one single temperature. So 500 to 700 degrees Celsius is the range, and the content can even as high as more than 90%. Okay. Now there is one example of how this rises cache property changes with the different processes. So first you can see on the A top left image, you can see this is the temperature and this is the temperature flow, how it goes 2 degrees Celsius per minute, it increased, and in approximately at 5 hours the maximum temperature of 600 hours is goes, and then at 2 hours it burned at 600 degrees Celsius, and then it cooled at 2 degrees Celsius per minute. It takes total 13-hour journey to rice as cache to get materials. But what they do, they get a rice as cache over here, right? So black RHA means uncontrolled combustion. This is RHA basically at 0 degrees Celsius. This is an RHA without cooling. So they just get the RHA out from the furnace after this particular burning. And then they allow, and the next phase, they allow the RHA to, cool down and they take out that particular material at 13 hours, right? So if you see on the B image, you can see rice as before heating, and then when you burned it and uncontrolled combustion at 400 degrees Celsius, as you can get from anywhere, any industry that is unburned, uncontrolled combustion, so you can get a black RHA, right? It means that there is a lot of unburned carbon is there, and when you process it, and you can get it at at 7 hours, and then just cool without cooling, you just get it out. You can get any gray kind of RHA. When you allow to cool, you can get a white kind of RHA. So these are the different forms you can get. And when you go for grinding of the RHA to improve the packing behavior, right? So this F15, F20, F25 are the different frequency and the time of grindings. So by that way, you can see the volume fraction and the density of that particle is increased, shifted towards then the finer size. So you can see that this RHA F25 frequency 25 give you the density maximum at 2 micrometer, sorry, 2 micrometer, not 2, 1, 10, yeah, 10 micrometer approximately. Okay, and you can see the peaks are shifted towards the finer particle size. Fine. So now if you see the fineness in terms of surface area, you can see that when you increase the grinding time, your average particle size is going to decrease, right? And your bed surface area is going to increase. And yes, if your particle size is going to decrease, your surface area is going to increase. And by that way, you can justify your results of workability. It may going to decrease if you decrease the if you fix the content of your liquid, your workability may going to decrease because the finer area increase and then they need more water. So accordingly, you have to, change the water content. Okay, so this is what are the results of the technical, these things, which is very important here. Okay, and the next is fresh and mechanical property of RHA. And as I discussed with you that yes, it may affect, it may change, right? With 10 to 15% is this particular replacement level where you can use that one. Okay, and you can increase the strength of the particular product. Okay, now next is the eco building material, because if the agro waste is not like only available for the concrete product, because as an building material, as an infrastructure, if you see only concrete is not solely covered. You have to work with another building product also, which may take weightage while making the building, right? So this is the another recent area of the research, the binderless fiberboard, where they are not using a binder. I will give you just an overview of that, uh, and this particular product, what how this is important for the as a building infrastructure product, right? So here, if they are binderless boards, because in if when you are producing the you know fiberboard with the binder, is having epoxy, and that kind of epoxy may in the external environment, it may affect the human health. So and the cost of that product is also increased when you are using an epoxy. The processing is increased, the time is increased to make the fiberboards. But once you are producing the fiberboard without binder, so it's an economic solution to produce the effective product for the building, right? So what is many fiber based industry increase their interest in the replacement of wood fiber due to the low cost of agricultural bioproducts available worldwide. So all the total costs depend on the location, quality, and harvesting costs, such as chopping, balling, or on-farm hauling of crops, among which balling is the most expensive, because there is a game of making the fineness, right? Making the fineness is then game, and the balling effect may increase the cost of the product. So you have to find an optimum size to reduce that particular product size. So therefore, using residual material to produce fiberboard is a cost effective and environmental friendly choice, which also consider the waste management hierarchy. The waste framework of this set prevention as the foremost priority of waste management, followed by reuse and material cycling. So they are therefore using the agro waste in the making the fiberboard, right? So Smaller amount of hemicellulose lead to a better resistance to water, as hemicellulose are hydrophilic and have a high absorption rate. Means that that particular agricultural waste in the organic state without burning, having different kind of, these particular these components, hemicellulose, low hemicellulose, extractives. These are the different components de- based on which your product, actually product behavior is depend, right? So the hemicellulose, if I give you the better resistance to water. So if you have a five means agricultural waste which is having a high amount of hemicellulose, that can give you the better resistance of water. Low hemicellulose content may lead to weak bonding strength. So those kind of fibers which has having a low hemicellulose, they will, limiting the durability of the product. The fiberboard production process serves to activate the lignin bonding ability. In turn, lignin contained in the wood or non-wood resources serves to bond fiber itself without any added synthetic or natural adhesive, right? Extractivities help to solve this drawback, but at the same time, their evaporation during hot pressing may cause delamination. So there are limitations also with this. So to produce this kind of things, we have forestry residue, we have agricultural residue, we have industrial bio waste also. But this forestry residue is nowadays not a good source, because we need to preserve the land, means we need to preserve the forest on the land. So we are not looking into this solution to use the forestry residue. And yes, industrial byproduct is there, and the next is the agricultural residue, which are people are using nowadays. So wheat residue is considered good agricultural waste for manufacturing the fiberboard. Here also, this residue can use. Rice straw is also used to produce fiberboard, right? So Vitis vinifera pruning have also been used for fiberboard manufacture. Knaf has attracted special interest in fiberboard production too, especially for its rapid growth. So it can reach a height of 3.6 to 4.2 meter during the growing season. So people are using this knaf because it is available in a higher quantity. So people can use that particular thing to produce the fiberboard, right? So what they produced, they produced low density fiberboard from this kinaf core, and they obtained a thermal conductivity quite similar to the insulation material generally used in construction like rock, wool, and also showing good mechanical properties and dimensional stability. So they are all about depending upon the sensible heat thermal storage kind of things. If you say it is not about the latent heat, it is about the sensible heat storage. Okay. So industrial byproduct is bagasse is in probably one of the oldest non-wood resources used for fiberboard production. It is a byproduct of sugarcane. We have studied this thing earlier, but it's considered just for making the fiberboard here. Now, fiberboard application, the construction industry makes extensive use of wood-based panel, which cause environmental problem both in terms of melting the high demand of wood and emission from the use of synthetic adhesive, right? Binderless fiber boards represent a possible solution for both the problems. On the one hand, the use of alternative fiber support the concept of forest protection, as I told you, that save the forest by looking into the waste of the agricultural land from the agricultural aspect. The absence of formaldehyde emission makes these panels particularly suitable for indoor use application, such as wall partition, false ceiling, and furniture, right? Because the epoxy presence of epoxy may affects the internal environment through their chemical reactions and may affects the health of human health. Okay, so this is the different images of fiberboard, and this is, you can see the difference in the appearance because of their fineness, because of their chopping, right? If you chop, because increase the chopping may increase the cost of the product, may also increase the quality of the product. Decreasing the chopping may change the appearance, may change the performance. So somewhere in between, you have to optimize, you have to engineer the requirement accordingly. Whatever is the requirement from the final product, accordingly you have an option. If you need fine surface, you have to do a more chopping. If you need a coarser kind of surface, not so important, then you can do a lower chopping, and the cost will also decrease accordingly. So this is all the aspect of using that. Now, if you see application of agro waste in construction sector, so as we have seen that agro waste as a whole, right, they are applying for the cement, concrete, right, mortar, These are the different concrete over there in the left side: engineered cementitious composite, ECC, self compacted concrete, high performance concrete, ultra high performance concrete, geopolymer concrete. So and other types of concrete as well, but these are the major areas where the agro waste is basically using. Next is the brick on the right side option. That brick also used from the agro waste. You can produce fire and unfired bricks. Nowadays, unfired bricks are more acceptable because of avoiding the CO2 emission during fire in the kiln to make them hardened. So unfired bricks are more good to make them thermally insulated, lightweight. Also, agro waste are used. So as you've seen that if bagasse is replacing, then specific gravity is less, then you get a good lightweight product. Then you have seen that also fiber board and acoustic and thermal insulation. To get those kind of benefits, people are using fiber board. So it is not like you are using agro waste. You can use agro waste only on concrete. You can use on in the different building materials rather than the concrete only. Okay. Now, to achieve the carbon neutrality, zero carbon dioxide emission from construction products, that we are doing. So why carbon neutrality is so important? So I'll just give you a brief that uh, they in the two in 2015 in a UN meeting, they developed these kind of some SDGs, Sustainable Development Goals. We have total 17 Sustainable Development Goals. From there, civil engineers directly or indirectly may this uh, contribute, right, in these SDGs. Therefore, you have seen that in the last 2 decades, research, their sustainability terms is more appealing or more appearing on the research, and most of the journals now, making their scope of publishing towards the sustainable, this particular word sustainable, rather than it is a building, rather it is a bridge, it is a material, it is hybrid field, but they are using this sustainability so that they can contribute towards these particular sustainable goals. And nowadays you can see that also in SCI, in Elsevier websites of and many journals, on the left side they wrote there they support SDGs. If you saw that, you can see they wrote there they support SDGs, and they show this kind of small icons in their image, in their screen also. So this is the change which is going on right now because of these SDGs. And as in civil engineers, we are more means attached with this affordable and clean energy, with decent growth, work and economic growth, with industry innovation and infrastructures, and this 11th sustainable cities and communities, and then responsible consumption and production. So here the 12th is basically related with the recycling product, waste product, right? A genuine use of the product, right? Durability. Then it comes sustainable city and communities, like more resilient structure, right? More facility to every people of community they get from that, right? Good health. And then industry innovation infrastructure, more resilient structure in the for to serve the people. And then decent work and economic growth, yes, it is relative with the economic cycle also. And then affordable and clean energy, like as we talk about this fiber board, thermal, right? Like that, people are working on the thermal storage material also, means phase change materials. This is the new research, not new, but people are working on this area aggressively to develop the phase change material concrete, PCM contained concrete, PCM contained mortar. So they are using that kind of concrete also to store the material, and that they are based on the latent heat storage. They are not, because concrete is based on the sensible heat storage, but these products are based on the latent heat storage. So this particular thing is directly support this affordable and clean energy. So we are somehow, from the research, supporting these SDGs, right? And in India, there are various schemes in which Satat Bharat, Sanatan Bharat, Sustainable India is one of the scheme that support the infrastructure related SDGs. So if we correlate this, how we are contributing, this particular thing with the SDGs, you can see here. So we by these different schemes, we actually supporting the different SDGs. So if you see the Satat Bharat, Sanatan Bharat, Sustainable India, you can see we want to create the gender equality, right? And because still there is a challenge in the gender equality, because at the contribution of this uh, this men and women is not equivalent in the civil engineering field because of the various problems, right? Because in this at the site there is not an environment, proper facilities available for human beings, so it is very difficult. You have to be very rough at the site, so it is difficult to survive at the site. So gender equality is very difficult to maintain, but still a challenge, and people are working on that. Clean water and sanitation, we are working on that. Affordable and clean energy, industrial innovation, sustainable city responsible consumption, climate action, and life below water. So this is also important when you are working on the ocean to make some structures. The marine life also affects because of that construction. So during that time, this particular aspects you have to take care in your research, right? Now, if we see the complete image of the sustainable development goals given by World Green Building Councils, that how this infrastructure, support the SDGs. So if you see on the first left, the third SDG is good health and well-being, right? So that supports by green building can improve people health and well-being, right? So this is something which is helpful for supporting the SDG 3. If you see the SDG 7, which is affordable and clean energy, so green building can use renewable energy becoming cheaper to run, because nowadays we are whatever energy we are using, that is comes from the thermal power plant, right? Some comes from the some fossil fuel based plants. But the coming future is based on the promotion or use of maximum renewable based energy, and this renewable energy, one of the source is sun. So you can use solar panel, you can use phase change material to store this thermal energy, thermal storage, to make the thermal storage, and then you can use that later on when you need, because store the heat actually in within them by changing the phase from liquid to solid or solid to liquid and releasing that at the same temperature. And then we have 8 decent work and economic growth, that building green infrastructure create jobs and boost the economy, so that is supporting that particular 8. And 9, industry innovation and infrastructure. So green building design can spur innovation and contribute to climate resilient infrastructure. So basically, innovation is a kind of, you can see that previously the architecture is, aspect is only on the, on the shape of the building, how it looks like, how the space is utilized. Only that kind of stuff were taken care by the architect. But nowadays, the new aspect came into existence, like, while designing the building, if it is a kind of summer, how to give the slant height of the roof so that you can avoid the direct entry of sun rays into inside of the building. When it is the this kind of winter, then how to increase the direct sunlight entrance into the house. So we can say, in conclude, we can say the orientation kind of thing. So people are, architectural engineering are more towards the utilization of these renewable sources to decreasing the amount utilization of the fossil fuels, right? So by doing so, this kind of aspects came. Then 11 is sustainable cities and communities. So green building are the fabric of sustainable communities and cities. Then 12, responsible consumption and production. This is the area where we are working actually. Means we all from the field of materials and structure utilization, that all we are working, because whatever you can say, if recycling material using into the concrete, we are using, recycle asphalt into the pavement, we are using waste material into that. So this is all about the responsible consumptions, all right, and production. So the production of fresh material will be decreased if you are using, the the waste material which produced on land. So this green building use circular principle where resources are not waste basically. So you are keep on using the material until the complete degradation, right? Nowadays new area also came into existence, that earlier the recycled product were used for making a concrete, and people were saying, researchers were saying, basically the strength is going to decrease because of the old paste attached with the aggregate, and the aggregate is also porous inside, so they absorb water, and that is also density is decreased, right, over a period of time, so that is giving a bad result. But nowadays what people are doing, the people are putting that into the carbonation chamber, and they are increasing the density inside, means based on hydration, they are improving the properties of basically recycled aggregate or paste, and then they are using again into the concrete, and they are saying that they are getting that results, that yes, the strength is increasing. So these are the some point, or some the ways to improve or enhance the use of waste material into the construction sector, right? The next is the climate action. Green buildings produce favor emission and helping to combat climate change. So we are, if we know that every year the temperature of global temperature is increasing by some of the degree, so to decrease that particular percentage, that is very important for every country to reduce the to improve to enhance the greenhouse green buildings, right, to decrease the amount of CO2 emission. So next is the life on land. Green buildings can improve biodiversity, save water resources, and help to protect forest. Means it is an indirect relationship of good infrastructure with the land, life on land. Then partnership, yes, through building green, we create strong global partnership, right, by doing so. Now, this is the global carbon emission target. Basically, in 2015 or 16 something, 15, we have this kind of chart where CO2 emission of every country in the area mapping is shown, where China is contributing more, India is lower, US is second, and Europe is the third one, and then other countries there. Okay, here they made a statement there recently. China gave the document where he said that because presently they are using the fossil fuels for producing for their working, so it is very difficult for them to sudden changed their all running infrastructure from fossil fuels to the renewable energy completely. So presently they are occupying 23% global demand of energy, means energy from the global energy demand, and that is based on the fossil fuels. And they are saying it is very difficult for them suddenly reduce the things. So up to 2035, we may utilize the 23, 24% or 21, 22% of the global energy demand. But after 23, 35, we almost replace our all existing culture of using the means working on fossil fuel to the renewable energy based, and from there 2035 to 2050 we will get the zero carbon emission from the country, right? Likewise, US also increased last year the global emission, but they are looking for that particular decreasing the carbon emission. Europe is going very well in decreasing the carbon emission nowadays. Very good research is going on in the Europe in the field of civil engineering also, because they are more towards producing the those kind of products which need lower temperature to make them product, so the carbon emission is less, and they are working on a green product also. So these countries are working. Europe is presently working very well, right, and India is also going towards decreasing the carbon content. But of course all the countries have to work on this 2050. And you know that this presently India also have some codes on which they are measuring the new buildings on the base to make the green buildings rating. So that also work is going on in that area. Many experts are there. Maybe you have heard from some speaker which gave earlier on this topic, right, how to measure the green rating of the building. So this is the overview holistic approach of what we are doing and where we have to reach. So these are the reference, and thank you.